As I continue with the regulated power supply idea, I've been working with the TNT transmitter as a load and using the regulated power supply as the power supply for the B+ on the tube. I do find that just as the PS3 specifications show, that it does run out of gas at the higher voltages. And I was not able to operate the transmitter above 350 volts. So at about 350 volts, even supplying the 40 milliamps that this small oscillator transmitter requires is really causing the thing to go slightly out of regulation. You can see it's getting about a 10 volt droop. Now, if this was an ordinary power supply with no regulation, it would droop even more. It might droop as much as 50 or 75 volts, but drooping 6 to 10 volts isn't too bad. We're getting a good note out of the transmitter. About 5 watts out with the 350 volts. If we were able to operate the transmitter at the full 500 volts at, say, 50 milliamps, now we're talking, more power. And this thing might actually be able to do closer to 7 or 8 watts output power if we were able to run it at the full 500 volts. Now, even 4 watts is effective when you've got close by stations or good conditions on 80 meters. And I will do a QSO using the TNT transmitter in this video. We want to try this thing on the air. It sounds pretty good, actually. When hooked up to a transmitter, you will notice a little bit of roughness, and that's characteristic of the TNT. You don't have a super pure CW note with the TNT compared to many other oscillator styles. Even though we have a DC on the filament and a regulated supply on the plate, there still is some distortion in the CW tone, but certainly useful on the air. A lot of fun to work with these simple transmitters. And they work a lot better when you have a good power supply connected to them. So the way the old timers used to do it is they would overdo the power supply. In other words, they designed the power supply to maybe be able to supply a couple hundred milliamps so that the little 40 milliamp draw of this transmitter would hardly tax the power supply at all. AC supplies were a thing by the late 20s, early 30s. AC power supplies with a transformer, some type of rectifier. Vacuum tube rectifiers were already in use by that time. So most guys just used a Type 80 rectifier for something like this. And the Type 80 would go into a choke input filter, and then an oil-filled capacitor and a good bleeder, and you'd have pretty good note on your transmitter. Again, these small one-tube transmitters during the Depression years were very important. People could not afford very expensive transmitters with multi-stages, shield boxes, big rack systems. That would come later on. Well-heeled amateurs can always afford the best equipment, but most amateurs got by with 1- and 2-tube transmitters, much like this. Where did I get this thing? The transmitter was sent to me by W6TOM, Tom, who actually purchased it at the West Coast Military Collectors Meet in May. So the transmitter was built by Hank Henry Brown, W6DJX. And Hank is still with us. He's 94 years old. He probably built this in the late 80s, early 90s. I don't have all the details. But it is tuned expertly, as you're going to find out later in the video. Some of the circuit details were covered in that original TNT unboxing video from last month, but I want to go a little deeper into the circuit. As discussed before, the tuned not tuned oscillator is a form of the TPTG, or tuned plate tuned grid oscillator. You may have heard that oscillation feedback is between the plate and grid capacitance of the tube. This is true, but it explains very little on how the circuit works. You may remember that with any self-excited oscillator, you need energy, that's the power supply, a frequency determining component, that's the plate tune circuit, an active component that converts power into gain, that's the tube, and finally, positive feedback, a portion of the output fed back to the input in a 0-degree condition, a 0-degree phase condition, or actually any integer of 360 degrees phase. Thermal noise, or the application of power as a transient, as with our CW keying, that kicks off the oscillation. In a power oscillator such as our TNT, more energy must be supplied from the power supply in order to keep the oscillation going when we're delivering more and more power to the load, our antenna, through the coupling control. Specifically for our TNT oscillator, the feedback loop consists of two tuned circuits, which are also by nature variable, basically plus or minus 90-degree phase shifters, and the tube's capacitance is involved too. The feedback loop is completed through the power supply connection. That ground path is the missing feedback connection that we seldom talk about with oscillators. Ripple here will go right into the path, causing all kinds of trouble from buzzing, squagging, which is a kind of RC relaxation effect. Anyway, you get a nasty sounding signal if you don't get this power supply stuff cleaned. Generally, the two tuned circuits must be tuned nearly to the same frequency, but the tank circuit of the plate must be the higher Q resonator. It also must be low loss because, remember, we're taking power from it to send to the antenna as well. So it has to have a very high loaded Q. And to get the positive feedback, the plate circuit must be inductive compared to the grid coil. So it must be tuned slightly higher in frequency than the grid tank to get the phasing right for positive feedback. So in general, we get 180 degrees through the tube itself, and then another 90 degrees from the plate tuning network. And then everything else that's left, a combined phase shift with the rest of the loop, including grounding, bypassing, power supply, the grid leak, all of that stuff, and that grid resonator that we wound. And that's how we obtained the remaining 90 degrees, producing the positive feedback condition. Our TNT can only meet this criteria over more than one frequency if the grid resonator has a very low Q, and it has to be resonant lower in frequency. Even then, the frequency range at which the TNT works well will be pretty limited. Fussing with the grid coil always pays off in signal quality with the TNT. Compared to the tuned plate tuned grid, with two fairly high Q tank circuits, the TNT will require more gain to maintain oscillation. And it's going to be more susceptible to power supply issues like ripple. Furthermore, the TNT will exhibit increased phase noise compared to the other types of oscillators, such as the Hartley, Colpitts, and tuned plate tuned grid. These shortcomings were accepted because the elimination of an expensive variable capacitor in the grid tank and a guaranteed oscillation and single control tuning, these were all very desirable characteristics for the beginner in 1930. Let's take a closer look at the construction. Some of you really like explicit instructions on construction, especially with coils. So here is the original George Grammer QST article from the early 30s, and a great online build resource from my friend Steve McDonald, VE7SL. Steve gets right down to the hows of winding those big coils. Let's take a little more critical look at the TNT transmitter build. The tube itself is a bayonet style. So it has this little feature on the tube that goes into the bayonet socket. There are many different styles of 4-pin sockets that would have been appropriate. Not all of them are this bayonet style. Some you simply push the tube in and it's a friction socket. The TNT coil appears to be an original type form. It's a black phenolic plastic with the green double cotton coated wire on it. Looks to be maybe number 26. We have a 10K dog bone resistor with a grid leak capacitor. That looks very nice, with a nice mounting system with brass hardware. A beautiful homemade terminal strip with period binding posts. Excellent. A standoff here that's holding the back of the variable capacitor also looks pretty good. The regular copper tubing coil would have been fairly standard. The use of a smaller link output coil, this is a little bit unusual. It's certainly doable, and he's going right straight to coax off that. At the time, they probably would have used the same wire, the same tubing for the output link. Notice that he's using square stock wire, not ordinary tinned number 10 or number 12 wire. That is square stock wire, and it's carefully bent around and soldered in place. Very symmetrical looking. You can still get tinned square stock wire. It's used in making jewelry of all kinds, and usually you can find something like that even on Amazon, believe it or not. You might have to get a couple spools of this stuff. And he's using different kinds of fork terminals. These are all soldered connections. Beautiful job. There's nothing too unusual about the construction. He's using the standoffs for the entire coil assembly. It's very important that this is made stiff. Sometimes people actually support the coil with a third standoff in the middle of the coil. I'm surprised at how stable this thing is. He's done a great job. Also, he's using quite a bit of the variable capacitor. I would have used fewer turns so that 80 meters would have been around here. Higher C, lower L would give even more stability. He's got it set in the middle. That's still going to be about 150 to 200 picofarads, even like this. But when meshed like this, it would be more like 350, 400, maybe even higher picofarads. So a little more stable with more C, less L. Also, I'm touching this coil. This coil is not insulated. This is hot to DC. This is called a series feed system. And you would get a shock if you touch this and ground. Shunt feed is also possible. It would take an extra capacitor to do a shunt feed system. Two expensive parts that you can dispose of if you use series type feed for the DC. So that's the rundown. All of the parts on the breadboard appear to be original, or at least parts you could get in the late 20s. The only one that kind of got my attention that it might be newer was the center tap resistor on the filament. I did dig out a 1933 Allied radio catalog. And as you can see, by 1933 at least, all kinds of voltage dividing resistors were available. So I would surmise that that is an appropriate resistor for the transmitter. That was the newest looking part on the set. Everything else certainly looked like it was 1920s feasible, but perhaps that resistor is maybe 1930 to 1935 type vintage. In construction, of course, it uses the porcelain type voltage division resistors, and they're certainly talking about that here already. So looks like it's a very, very period correct build, the TNT transmitter. Also, the tube that I stuck in, being an ST style, the more appropriate tube might be the globe style or the 210 type tube. Of course, you can do more things. You can extend this shaft so that the dial is further out, making tuning easier. You could use a vernier dial. You could have a metal front panel, which of course would improve things drastically. So here's the question. How does one know that you have indeed optimized that grid coil? How do you know when you've got that grid coil at the right self-resonance? And how can you verify it? Well, of course, trial and error is how most people do it. But here's a way to check. Now, I've got this hooked up to a dummy load. I have the power supply set for 350 volts, and we're in the current position, okay? Voltage, current. I have the scope hooked up to the output so we can look at the quality of the sine wave. Hopefully this thing puts out a sine wave. And we're looking at the power output meter. We know this thing puts out about 4 watts with 350 volts. If that coil, that grid coil, is correctly set, we should be able to detect a dip in the plate current around the frequency that we're interested in. Now, it's not going to be right exactly on frequency, but it will be in the band. And the band we're interested with 80 meters is 3.5 to, say, 3.6 megahertz. So let's hit transmit and let's tune the single dial. Remember, there's only one dial on this thing. And let's see what we get. Okay, we have a nice sine wave. We can see that. We're putting out 4 watts. I'm going to tune through resonance. Oh, yeah. You see how I'm dipping the plate. And you'll notice when you hear the little blip on the receiver, I'm going past our frequency. This TNT is expertly set. The grid coil is almost perfect, giving us a good dip, good output on the frequency of interest. So that's the secret sauce to this whole video. Now you know how to tune your TNT. I've got my power supply set for 7.5 volts, which is the filament voltage on a type 10, and it's drawing about 1.25 amps. Now, usually these were powered by an AC 7.5 volts, not DC. But of course, the transmitter doesn't care if the filament is heated by DC or AC. So we'll stick with the DC here. I have been working with the Heathkit high voltage regulated power supply, the PS3. This is a good example of something you might do with a PS3 to power up a free running oscillator. The tuned not tuned, or the TNT transmitter, is a free running oscillator. It's not a Hartley, it's not a Colpitts, it's a tuned, not tuned plate oscillator. And I say a plate oscillator because the high Q coil is in the plate circuit. The low Q coil, which is in the grid circuit, is broadly tuned. And the feedback path is through the tube, from the plate to the grid. And with the phase shift you get on the output tank, you can shift it around so you get positive feedback and it will oscillate. Let's see if we can get some power out of this thing. I'm going to set the regulated power supply's voltage. Okay, right now it looks like it's set for about 325. Let's see how much current it draws at that. Looks to be about 40 milliamps. I can get a meter in there and we can get a more accurate measurement than that. So if you multiplied 325 volts times 40 milliamps, that would be the input power that the transmitter is taking. Now, how much output power are we getting from the oscillator? Looks like about 3.5 watts. It's still warming up. About 3.5 watts. Again, we know we're limited in current with the Heathkit. It doesn't seem to want to put out the amount of current that you would think at the higher voltages. Let me go down to 300 volts. Try it again. I guess that's just the way it's regulated. Let's try for 350. And it's still in regulation, at least the regulation that this thing can supply, which is not great. Just about 4 watts output power into a dummy load. Well, with 4 watts, we should be able to make a contact. So now I'm going to hook up a transmit-receive switch, and we can use it with my Watkins-Johnson receiver, We're set for 3.550 megahertz or 3550 kilohertz. I want to try to make a contact with the TNT. I've set up a schedule with a good friend of mine who lives in Ossipee, New Hampshire, and he also has a TNT transmitter. His is a little fancier than this. It's a push-pull TNT with 2 tubes. It is a breadboard. So I'm going to try to make a contact on the air with him. It will be near vertical incidence since we're only talking, I would estimate about 100 miles. I'll give you an exact distance between stations, but it'll be near vertical incidence. So he isn't that far away, so we'll have to pick a time that we think we're going to get a good bounce on the transmitter. Now this thing tunes very fast. Remember, we had to have the small capacitor off the tank in order to do the fine tuning. Okay, this is characteristic of a free-running oscillator. You definitely get some changes if there's vibration or if you come in contact with the coil or come close to the coil. You do have to be very careful. High voltage actually on the coil. You don't want to come between this and ground or you'll get a severe shock and possibly a lethal shock. So we have to be very careful with high voltage. Also, even touching the main tuning dial can mistune the transmitter. So you can see isolation using a real metal front panel and so on. These are all things that would help. A vernier dial would help. The pattern capacitor off the side was the way that Hank chose to do his fine tuning. And he extended that so he can do the tuning without interfering with the coil and changing frequency. It's a pretty clever way of getting on frequency with the transmitter. So we're going to run it like this with about 4 watts output power. We're using the regulated power supply at 350 volts. Let's see what the current drain is at 350. That way we can estimate the input power. Yeah, it's still about 40 milliamps. Okay, let's take a little more critical measurement here. So that coil is hot for DC, so we want to keep our hands away from it. It's built per the schematic, and it is not shunt fed, it's series fed. And you can see the difference in these two schematics between series feed and shunt feed. Shunt feed, of course, is safer because the tuned circuit is actually grounded. Okay, so we got 355 volts open circuit. Now I'm going to close the key and we'll see what the regulation is on the Heathkit supply at 40 milliamps. Not very good, guys. That's pretty pitiful. But again, we're beyond the limits, I think, of the power supply at this high voltage. Now let's check the current. 46 milliamps. 46 milliamps, we have our voltage, we have our current, and we know we're putting out 4 watts. Okay. Sounds like Larry might be tuning up. I think I hear him. Tonight we're on the air on 3550. I've asked my friend Larry, NE1S, to get on frequency. And we'll see if we can make a TNT to TNT contact. I think that was him. Sounds like he's on frequency. Okay. Okay, he's using a push-pull TNT with a pair of 45s. Okay, so there we are, a contact TNT to TNT. His TNT, a pair of 45s in push-pull. My TNT here, this is Hank's TNT, a single type 10 in a single-ended TNT oscillator.